Swayam Prabha. Digital India. Educated India.
Dear learners, welcome to this course Advanced Thermodynamics and Combustion. We are in the first module, that is review of basic thermodynamics. So, on this module we have following topics which we are going to discuss in the subsequent lectures. The first lecture we will be discussing about temperature and zeroth law of thermodynamics. It will be followed by the first law of thermodynamics, which involves the introduction of work and heat transfer concepts. Moving further, we will have the third lecture on this module, that is second law of thermodynamics involving heat engines and refrigerator or heat pumps. Now, we are in the first lecture and the title of this lecture is temperature and zeroth law of thermodynamics. On this lecture, we are going to discuss the following topics. One is macroscopic and microscopic approach. Then we have thermal equilibrium and concepts of zeroth law. Then we have concept of temperature and its measurements. Then we are going to introduce simple thermodynamic systems and in particular hydrostatic systems. Another point that I would like to emphasize here is that in the basic thermodynamics course we have covered all of them in some sense, but however, here our approach will be little bit different in a sense that because it is advanced thermodynamics course and we are going to treat the same concept with different philosophy, and everywhere we will try to see try to involve more towards the mathematical concepts apart from the physical background. So, let us start the first segment, that is macroscopic and microscopic approach. As the word indicates, macroscopic is a global phenomena, microscopic is a kind of a molecular phenomena. So, in a same sense we deal this thermodynamics course either in a global phenomena or in a large scale situations, and other way we are looking at this microscopic approach in the molecular level, where we take the information at micron size or molecular size and try to grasp the information about the global properties. However, both the approach have their own advantage and disadvantage, but at the end of the analysis we are going to conclude that both lead to the same inferences. So, this is the overall picture of this particular segment, but before you go deep into them, let us see that what does this word thermodynamics means. It is nothing but the science of energy. As you see that energy is available in many forms, like we have thermal energy, we have electrical energy, we have mechanical energy, we have hydro or wind energy, nuclear energy. Energy is also available in the form of chemicals, that is in the fuels. Energy is also available underground of earth, and we call this as a geothermal energy. We also have solar energy. So, there are multiple sources of energy and they can be linked together. Now, when I say this energy when it transfers either in the form of work or heat, which is the essence of this course, and these work or heat interactions, they can be linked together, and that is nothing but the science of energy. How we are going to link it, that is the theme of this particular topic. Now, when you say this the energy conversion, it can be applied to many applications like power plants, where we have steam or we can have gas based power plants. We can have IC engines, internal combustion engines, aircraft engines. We have also many cooling systems such as refrigeration, air conditioning, and human body itself is also a kind of the source of energy. Now, moving further to our basic topic, that is macro and microscopics. So, this particular picture shows that there is a container that contains this gas. Now, when you deal this macroscopic in a gross sense, we can say that the specifications of this gas in a thermodynamic viewpoint can be represented as its pressure, and it occupies certain volume, and it has some temperatures. So, this is what we call as a macroscopic approach in defining the state of this gas. Now, in same sense, if you want to go to microscopic approach, then we can view this entire gas to infinite number of molecules, and each of them is placed at a particular locations. They are specified by their coordinates xi, yi and zi in space, and correspondingly each molecule has its own pressures in x, y, z directions, and also similar informations can be represented for volume and temperatures. Now, when you deal with these individual molecules and try to grossly integrate to the entire systems, then it becomes a macroscopic viewpoint. So, this is the gross meaning of microscopic and macroscopic approach. And another, before you go further, let us understand some basic terminology, which in fact we all know from the basic thermodynamics course. First thing is system. System is nothing but the region within the arbitrary boundary in which our attention is focused for investigations. So, as you can see in this figure, we can draw a system where we want to study what is going on within the system, but this system is limited with respect to surrounding by a boundary, and this boundary there are possibilities that we can think of this boundary as a fixed boundary, or we can say it is a stretchable boundary or moving boundary. So, what depending on the requirement, we can say that system and surrounding, they constitutes, system and surroundings are separated by a boundary, and both when integrated together, then we call them as a universe. Now, again another topic of discussions in the basic thermodynamics course was that system can be closed systems or an open systems, or it can be third category, it can be isolated systems. When you say closed systems, then we say that there is no mass interactions, but there is a possibility of energy interactions. So, it is a fixed mass system. So, this can be viewed as a piston cylinder arrangements where you have a constant mass. The mass can this piston can compress this gas or expand this gas. So, depending on the motion of the pistons, we can say the gas inside the cylinder is either compressed or expanded, which means that there is some energy interactions that happens between the systems and this and surroundings across this boundary. But when you say in open systems, there we relax this restriction of mass. So, there we say both mass and energy interactions are possible. So, as you can see that some flow can enter into the systems and the flow can come out. Similarly, energy can enter and energy can go out. So, there is no way of specifying this volume, but rather we say we can say that there is a fixed volume or control volume where our attention is focused. And when the third category, when you say it is in isolated systems, both system and surroundings, between the system and surroundings there is no mass and energy interactions. Then we move to more details on microscopic and microscopic approach. So, when we start our thermodynamics viewpoint, that means when we are putting our attention focus to a particular systems, then we have to think that what way we should proceed, whether it is a macroscopic viewpoint or macroscopic viewpoint. So, based on that we say that when a system is chosen, the next step is to describe the quantities related to behavior of the systems and its interactions with surroundings or both. So, that way we can say that there are fundamental descriptions in which we can say we have a macroscopic description, means that we need to specify some measurable properties of the systems and with an assumption that internal structure of the system and the calculations of system characteristics. Then another significance of this macroscopic approach, that it assumes the Newton's law of motion, that is the fundamental laws of motion. So, Newton's law of motions talks about force and acceleration, that is mostly, and passively it also says that is the what is the mechanical energy available for a systems, and that is in the form of kinetic and potential energy. So, with this we have some energies that is taken care when we have the macroscopic approach. In addition to this, we also have another independent properties, that is the macroscopic quantities that gives the property what we call as a temperature, and this temperature is nothing but the concept of another bearing to the energy of the systems and what we call as internal energy. So, ultimately in a macroscopic viewpoint, the thermodynamic coordinates mostly relies on Newton's law of motions and the concept of internal energy. Now, having said this, again if you try to emphasize the Newton's laws of motions, it has two essential components. One is force, other is kind of acceleration or motion. So, when I say when we try to correlate those Newton's law with respect to macroscopic situations, then we must relate to the thermodynamic systems. So, let us say that we have two coordinates x and y which are independent in nature, and x represents the generalized force and that comes from the Newton's law, but we view this gas as a pressure of the gas in a thermodynamic viewpoint. Another category of our parameters, that force is related to accelerations, or in other words initially the body is in motion. So, force is related to displacement, and this displacement with viewpoint of thermodynamics we call this as a volume. So, in a sense that with same concept of Newton's law, the macroscopic view of thermodynamic coordinates of a system can be specified as a function of pressure and volume, and they are related to each other. That is one category. Another category I have already mentioned, that which is independent to both, and that is the temperatures. So, both x and y coordinates and side by side with temperatures, they define the conditions of a system, and when the conditions of the system does not change, we call this as a equilibrium state. and this particular equilibrium state gives the concept of zeroth law, and in the subsequent slides we will talk about mostly on thermodynamic equilibriums, and where we can say that how zeroth law is related to the thermal equilibrium. So, the existence of equilibrium state depends on the proximity of other systems and nature of the boundary wall which separates between these two systems. So, to analyze further regarding thermal equilibrium and zeroth law, let us consider this particular figure. What has been shown here is that there are two figures. One is the system A and system B, which is separated by a adiabatic wall. Other is same systems A and B is separated by a diathermic wall. The word adiabatic refers to the fact that there is a communication of heat is not possible, but in a diathermic wall there is a communication between the systems with A and B is possible through heat transfer. So, what it refers or what it refers to our understanding is that if you say the first figure where system A and system B are separated by an adiabatic wall, what I can say is that if you have some state of the systems, that is here I will say values of x and y, that means it can be generalized force or displacement, or in terms of thermodynamic coordinates it can be pressure and volume, and for system A and system B they are defined by these parameters, and for system B those parameters are like y dash and x dash. So, when there is a adiabatic wall, which means there is no communication of the system A and system B is possible through this adiabatic wall. So, it means that the system can retain all possible values of x and y, and system B can retain all possible values of y dash and x dash as long as this adiabatic wall is there, and it is sufficient to withstand the stress that is developed by system A and B, and of course, at this same time there is no communication of heat is in between A and B. But looking for the other figure where the system A and system B are separated by a diathermic wall, we can say that only restricted values of x and y are possible for system A, and only restricted value of y dash and x dash are possible for system B, because there is always a communication between system A and B through heat transfer. And this particular mechanism we call it as a thermal equilibrium. Since we have put this word adiabatic and diathermic, so we say and the change in the system that happens is through the heat transfer, then the word thermal equilibrium fits to this philosophy. So, we can define this thermal equilibrium is a state that is achieved by two or more systems, and it is characterized by the restricted values of coordinates of the systems after they have been in communication with each other through a diathermic wall. Now, moving further, let us complicate a bit further, that we will bring in addition to the system A and B, we will bring another system into picture, that is system C. So, here we view this entire systems, that means we put both diathermic wall and adiabatic wall into picture, and they are arranged in a particular fashion. So, in a first figure here, what we say that system A and system B are separated by an adiabatic wall, and both integrated together they are separated with respect to system C by a diathermic wall, which means we can sense is that Since system A and B are communicated by system A and B are separated by a adiabatic wall. So, there is no communication between A and B, but this communication between A and B can be possible through this system C. That means, system A can interact with system C, system B can interact with the system C. In other scenario, if the locations of this adiabatic wall and diathermic wall is changed. So, it means that system A and system B are separated by a diathermic wall and both integrated together are separated with respect to system C by an adiabatic wall, which means that it is always possible system A and system B can come into the equilibrium, and there is no communications between this A and B of integrated system with respect to C. So, in this case equilibrium can be achieved between A and B, but where in this case the equilibrium can be achieved, in the first case the equilibrium can be achieved for A and B through the system C. So, this is the most essential concept of thermal equilibrium and Zeroth law, which says that the two systems are in thermal equilibrium with third, then they are also in thermal equilibrium with each other. And it was initially proposed by scientist R. Flower, which is in the year 1931. And in fact, why this word Zeroth comes into picture here, because this since it was proposed in the year 1931, prior to this already first law and second law was developed, and the first law was proposed in the year 1842 by Joule, and second law was proposed by Carnot, which is 1824, and they have their own understanding and viewpoints. Since we need to follow a logical sequence, then based on this the fundamental understanding was there that we will put this concept of thermal equilibrium and Zeroth law as thermal equilibrium as Zeroth law of thermodynamics, because it gives the concept of temperature, and subsequently that concept of temperature was utilized in for first law and second law in the subsequent years. So, that is the reason the word Zeroth law comes has its own significance. Then let us move to the further inferences that we get out of this Zeroth law, that is thermal equilibrium. Anyway, first point that gives the concept of Zeroth law is the thermal equilibrium. Then while understanding this concept of thermal equilibrium, if you want to quantify, then the word temperature drops in, and in a layman's sense it refers to the degree of hotness or coldness of a microscopic object. Okay. But the scientific understanding for this temperature can be interpreted through this thermal equilibrium, which means that we need to plot them graphically, and to understand this thermal equilibrium we must say that all the states are in same temperatures. So, in other words, graphically this same concept can be interpreted by representing in graphical form, and we call this as a isotherms. So, isotherm represents locus of all points representing the state in which a system is in equilibrium with one state of another systems, and in fact it is a continuous curve. So, bringing the same concept here, if you understand this is a system A and this is the system B, and for a given set of conditions, that is first condition 1, we can say the system was initially at state point y 1 and x 1, then it moves to y 2 and x 2, it then moves to y 3 and x 3, and all, and when moving these coordinates from one point to other, it is in thermal equilibrium with respect to its surroundings. So, that means we can represent this as a continuous curve, and as if there is no change happens, that means system undergoes a change of state without disturbing to the surroundings. Now, this happens at one particular set of conditions, that is 1. Similar things it can be represented for condition 2 and 3. In similar way, we can put same logic for the system B for a set of conditions of 1 dash, 1 2 dash and 3 dash. So, to understand the characteristics of isotherm, we must say that the system property, which is a temperature, and it determines whether a system is in thermal equilibrium or not. That means, we can quantify this temperature with some number that will tell us whether the system is in thermal equilibrium with other systems or not. Now, we gave the concept of temperatures or thermal equilibrium through this diathermic wall, but always it is not necessary that you should use the diathermic wall. So, for that things, what we see is that we use some kind of mercury or some kind of liquid which can bear this the properties of this diathermic wall, and which can measure or record the temperature change through while it is in equilibrium with the other with its own surroundings. And such a device we call this as a thermoscope, or many times we interpret them as a thermometers. Ultimately, what it indicates the equality of temperatures corresponding to one particular isotherms of the systems. Now, to quantify this, the first point we mentioned that in a layman's sense it gives the hotness or coldness of the systems. So, ideally people refer this hotness because it is hot, and that is hot because it is with respect to some temperatures, and that point of time the concept was the ice point and steam point. So, they were treated as a very basic reference temperatures, and with that respect people try to quantify this. Now, if you similar concept if you introduce here, that when we say we have plotted various isotherms for a system undergoing in different change of states, we can locate one particular point which will actually define the reference point, and that reference point was chosen as the triple point of water. Now, in the same xy plot where y is your y and x are the two independent properties involving Newton's law, or it can be pressure and volume. So, based on that we can locate one particular temperature on this entire set of isotherms, which we can say is nothing but the triple point of water. And for this triple point of water, we can define the set coordinates as x T p and y T p, and that is chosen as the arbitrary, that is chosen as the reproducible state at a fixed temperatures. So, what does this triple point of water means? Here we have situations, we have a thermometer bulb and it is put in a some medium or in a conditions in which we can say that which actually measures the triple point, that is 273.16 Kelvin, which means that this thermometer bulb is in equilibrium with this complete systems involving water, ice and vapor, and at this particular conditions, that is 273.16 Kelvin, this we can say all the state of water, all the three states are in complete equilibrium, or all the three states can coexist together. So that was the basic point, or one broad sense of viewing these reference temperatures, and in many situations people also interpret this steam point as 100 degree centigrades as reference, and based on this we have different scales were proposed, and these scales was now commonly called as centigrade scale or Kelvin scale. So, what does this two scales means? That when you say centigrade scale or Kelvin scale refers to the absolute temperatures, where the view was that it is referred to the absolute zero temperature, that is at that temperature all the reference coordinates of temperatures were calculated. And where when you say centigrade scale, it assumes that we have ice point, we have steam point. Based on these things we can see there is a rise or fall of mercury in a particular device, and we call this as a thermometer. Based on this rise and fall of mercury, we quantify whether it is quantify the temperature of the system. Now, apart from this, different countries use the philosophy of centigrade or Fahrenheit. In fact, the analogous to centigrade, there is another scale, we call it as Fahrenheit scale. Here only the magnitude of number changes, where and means that in a Fahrenheit scale the ice point and the steam points, they are different, and based on that we can have this coordinate. So, ultimately there are two scales which relies on ice point and steam point, that is centigrade and Fahrenheit scale, and there are two scales that relies on the triple point of water, that is Rankine and Kelvin scale. So, the corresponding relations between the Rankine and Kelvin scale can be written as this. This is the standard relations that can be used in our day to day life. For example, if you want to specify a temperature which you know as in Kelvin scale, and when you multiply into 1.8, we will get the temperature in the Rankine scales. So, this is the relation between Rankine scale and Kelvin scale. Correspondingly, there is a relations between Fahrenheit scale and Rankine scale. We can have relations between Fahrenheit scale and centigrade scale. Also, we can have relations between centigrade scale and Kelvin scale. Then we will move to the next segment of our lecture, that is simple thermodynamic system. So, from our previous understandings, we say that any state of the systems can be represented by its coordinates, and we call these as a thermodynamic coordinates with respect to macroscopic approach. And when this coordinates changes, we call this as a change of state, and when the system is not influenced by the surroundings, we call this as a isolated systems. So, that means the interaction between system and its surrounding takes place when there is a change in the system. So, we also know that for a simple system to exist in equilibrium, there are three types of equilibrium. First is mechanical equilibrium, and there we say that there is no unbalanced force and torque in the system. But this mechanical equilibrium does not include the change or reactions that is happening within the internal structure of the systems. So, if that happens, thermal equilibrium is not possible. So, thermal equilibrium is possible only when there is no change in the coordinates in the systems. That means, system is in the mechanical as well as the chemical equilibrium. So, ultimately by clubbing all these three equilibrium conditions together, that is mechanical equilibrium, chemical equilibrium and thermal equilibrium, we represent the state of the system as a thermodynamic equilibrium, in which we say that conditions of all the three types of equilibriums are satisfied. That means, in a mechanical equilibrium there is no unbalanced force, in a chemical equilibrium there is no reactions, and in a thermal equilibrium there is no change in the temperature. A thermodynamic equilibrium exists when all the three equilibrium conditions are satisfied. Otherwise, we say it is a non-equilibrium state. Then the philosophy of the equation state was introduced, which means that a system that entire systems can exist either in the solid phase, liquid phase or gas phase, or when you say liquid and gas, we say it is a complete the fluid state. So, based on that, the thermodynamic coordinates bears certain relations. Those relations are between pressure, temperature and volume. So, in order to change the state of the systems, B and T can be varied independently and corresponding equilibrium pressure can be determined. Similarly, P and T can be chosen to obtain V at the equilibrium. What it means? Pressure and volume, they can be integrated together. That means, when there is a change in the pressure, there is a change in the volume and vice versa, and temperature can be treated as an independent properties. And when we define these particular states involving pressure, volume and temperatures, we call this as a equation of state. And in particular, we have this equation of state for gas, when we call this as a either ideal equation of ideal gas equations, or it can be interpreted to with respect to van der Waals equations when you deal into the molecular approach. But however, when you deal with the liquids, only pressure volume relations are possible, because we require only these two we require the coordinates of pressure and volume, and all these things happens for wide range of temperatures. Then after these thermodynamic systems, then we will move to the hydrostatic systems. So, prior to this, why the word hydrostatic comes into picture? Earlier we used to say it is a thermodynamic systems, now we say it is a hydrostatic systems, because we deal with the behavior of a complete state of structures. That means, a system can exist in the liquid phase, gas phase, or it can be mixed of both, or if there may be concentration of the change in the mixture, or it can exist in different phase. So, depending on this, for complete set of understandings, we call them as a hydrostatic systems. Now, within the domain of hydrostatic systems, if you specify the particular characteristics, for example, when you say pure substance, which means it is a single chemical compound, that is solid, liquid or gas, or it can be a two phase mixture of all three. Then we can have a homogeneous mixture of different compounds, that is mixture of inert gases, chemically active gases, mixture of liquids, solutions. Then we can have the heterogeneous mixture of different gases which are in contact with liquids. So, all these three situations follow under the common domain, we call this as a hydrostatic systems. And in fact, in our entire courses we will be dealing with all these how to address all these conditions of the systems and in terms of pressure, volume and temperature. So, another important segment of hydrostatic systems is that we say that pressure, volume, temperatures are three independent quantities and they need to be correlated. Now, to specify those systems, we must have an understanding that how to quantify that. To quantify them, we have to rely on certain mathematical concepts, and that is nothing but the fundamental theorem of partial differential equations. And in general, if you say that there is a parameter z which is a function of x and y, we can write the exact differential of z, that is dz, as is dou z by dou x with respect to y into dx plus dou z by dou y with respect to x into y. Now, in another situation, if we consider a function f x y z is equal to 0, there are two relations that comes out among x and y and z. First one is the dou x by dou y with respect to z, dou y by dou z with respect to x and dou z by dou x with respect to y, and when we multiply them it is -1, and from this relation we can have another relations as well. And in fact, why I gave these relations, because we are going to rewrite our pressure, volume and temperatures for these situations. So, here we have said that we have three parameters: pressure, volume and temperatures, and pressure, volumes can be coupled together and temperature can be independent in nature. Okay. So, for that we can define these hydrostatic systems mathematically. So, there are four possibilities, in fact 3 possibilities which we can write. That means, volume can be represented as temperature as a function of pressure, pressure can be represented as temperature and volume, temperature can be represented as function of pressure and volume. So, accordingly, the exact differential dV, dP and dt can be determined. Again, from the third relations, that is, we can think that f of pressure, volume and temperature, if they are function of 0, they are equal to 0, then we can have this reciprocal relations, dP by dV, dV by dt and dt by dP, and they are, for each cases the temperature, volume, pressure and volume are held constant, and when we multiply them it becomes -1. So, we are going to use these 4 relations exhaustively in our all subsequent derivations or informations. Now, based on this, for an hydrostatic system, the first property that we are going to discuss is the volume expansivity. So, it talks about the how volume changes with temperature by maintaining pressure constant. So, this parameter is represented as a beta, which says that it is the ratio of change of volume per unit volume to the change of temperature when the change occurs at constant pressures. And based on this unit, we can say it has a unit of which we call as a reciprocal of temperatures. And in fact, the beta is always a positive number except from specific cases, and in fact, it is seen that this value of beta is insensitive to the change in the pressure and it varies only slightly with temperatures. So, hence it can be regarded as a constant for a particular gas or liquid or substance. The other property that we are going to discuss is isothermal bulk modulus and isothermal compressibility. The first quantity, that is isothermal bulk modulus B, is defined as the ratio of change in the pressure to the change in the volume per unit volume when the changes occurs at constant temperatures. So, this you can write this expression mathematically as B is equal to minus B into dou P by dou V at constant temperatures. So, here you can see that pressure and volume, they are reverse relations, that means pressure, increase in the pressure will lead to decrease in the volume and vice versa. So, in order to make this B as a positive number, so a negative sign is introduced here. Similarly, in correlation we have found out another correlations that can be derived as the reciprocal of B, and that we call this as a isothermal compressibility. This particular parameter was mostly used when you deal with the speed of sound, and in fact, when you say we use this in the compressible fluid mechanics or compressible flow, and it is nothing but it is reciprocal of this isothermal bulk modulus, and it is represented by kappa, that is equal to 1 by B, and that is equal to minus 1 by B dou B by dou P at constant temperature. Now, let us recall our understanding that how both volume expandivity and isothermal compressibilities are related. So, here we are going to apply the first relations. That first relations is between pressure, volume and temperatures, and that is nothing but the reciprocal relations. If we say F P V T is equal to 0, and that this equation was formed, where dP by dV at constant temperature, dV by dt at constant pressure, when they are multiplied, it gives rise to negative of dP by dt and constant volume. And we have to recall the parameters, that is beta, kappa, and from these two things, from these two parameters, one can find out the ratio of beta by kappa, and that is nothing but dP by dt at constant volume. Then when we are going to use it here, we can find this. What does means that we again start with another relations, where your P is your function of temperature and volume. We can write this dP by dt at constant volume, then dP by dV at constant temperature dV, and from this we can say at constant volume. So, this term goes to 0. As a result, we write dP is equal to beta B by kappa into dt, and from this we can have relations between the pressure change, that means from final pressure and initial pressure, and for a given substance for which we know beta and kappa, and if a system changes from the final temperature Ti, initial temperature Ti to final temperature Ta, then we can find out what is the change in the pressures. So, based on this concept, let us see one important problem, that is what is the problem which states that a mass of mercury at standard atmosphere pressure and temperature, that is 15 degree centigrade, is kept at constant volume. That means, initially the condition was 15 degree centigrade and atmospheric pressure. Now, what happens that at constant volume the temperature was raised to 25 degree centigrade. So, we are going to find out what is the final pressures. So, we have to recall our very basic understanding, which we says that we have to see from the last slide we derived this expression dP is equal to beta by kappa dt minus 1 by kappa v dV. So, here what happens, the system is at constant volume. So, dV goes to 0, then we can integrate these equations. So, we can write it as integration of dP, that is from Pi to Pf, and that is nothing but equal to beta by k integration of dt Ti to Tf dt, and we do not know the value of beta by k kappa. So, from this we have to use the data table, that means any thermodynamic book will give you this value of beta and kappa, and for mercury this value I can note down as 1 beta is equal to 1.8 into 10 to the power minus 4 Kelvin inverse, and kappa is 4 into 10 to the power minus 11 Pascal inverse. So, from this we can write P f minus P I is equal to 1.8 into 10 to the power minus 4 divided by 4 into 10 to the power minus 11 into T f minus T I. So, T I is given 15 degree centigrade. Then from these equations when you put this equation here, and Pi is your, so Pi is equal to 1 atmosphere, which is nothing but 10 to the power 5 Pascal. So, by putting Pi and Tf, we can say the final pressure will be about 452 atmosphere. So, which means that we require 452 atmosphere to change the temperature by 10 degree centigrades, because 25 minus 15 is 10 degree centigrades at constant volume. So, approximately 452 atmosphere pressure is required to change the to raise the temperature of mercury by 10 degree centigrades by maintaining constant volume, that is most important. The next problem is about this isothermal compressibility for air at 0.8 atmospheres. So, this is also a simple problem. We have to start from the basic definitions. What is the isothermal compressibility? That is kappa, and that is nothing but 1 by V dV by dP at constant temperatures. So, here it is, we have used this working fluid as a air. So, we say P V is equal to R T, and this equation can be written as P V is equal to R bar T, where and 1 by V is equal to P by R bar T. From these things we can write dP, what is dP by dV at constant T, that is nothing but minus R bar T divided by P square. And when you put this equation here, kappa is equal to minus, and 1 by V we can write P by R bar T, dV by dt is equal to minus R bar T by P square. This gets cancelled, P also gets cancelled. So, kappa, which is isothermal compressibility, is equal to 1 by P, that is reciprocal of pressure. And here pressure is given as 0.8 atmosphere, which means that kappa would be 1.25 atmosphere inverse. So, this is all about the calculation of thermodynamic properties of a substance. With this, I will conclude the lecture for this class. Thank you for your attention.